notes, that handwritten notes that Andras said he would Xerox and distribute. So if you don't want to take notes, now's a great time to stop before you wait. No, Jungle, you should do this. We promised we would have them for the web. But, so there'll be at least 2 versions out there. Okay, so at any rate, you know, now the homeomorphism type of smooth four manifold, so it's an important theorem of Friedman that the homeomorphism type of a smooth four manifold is determined by the intersection form. In other words, by its cup product structure. So, for example, here's a challenge. Classify all smooth four manifolds that are homeomorphic to the K3 surface. It's something we don't know really much about. Okay, so the tool that I want to talk about that we're going to use to study these things is a Seiberg-Witten invariant. And really what I'd like to talk about today is how to use gluing theorems to calculate Seiberg-Witten invariants, but that's probably not a good place to start. So what I'm going to do is I'm going to talk about Seiberg-Witten invariants, and when I say talk about them, that's really about all I'll do. And but it's not so important that you, well, I shouldn't say that. Am I being videotaped yet? Of course, it's important to understand everything, but it's not so important for the sake of my lectures that you understand details about the Seiberg-Witten invariants, more how they get used. Yeah. So, so let's begin somewhere. So suppose you have a smooth compact four manifold, just smooth four manifold. And its tangent bundle, Tx. So if you put a metric on X, then its structure group becomes SO4. So now SO4 is not simply connected. Pi 1 is Z2. So it's got a double covering group. The spin 4. So, and that's it's important that that's isomorphic to SU2 cross SU2. A spin structure on X. So let's denote the frame bundle, so the principal SO4 bundle associated to the tangent bundle, by Px. So Px is the frame bundle. And a spin structure on X is a bundle over X whose a principal bundle with structure group spin 4, which is a double cover of this. So, it's a bundle whose fiber is spin 4. And which is so this is a double cover on fibers. So now if you have a spin structure, then you can form associated bundles. So they're the spin bundles, S plus minus, which are rank 2 complex vector bundles that are associated to this So, and the plus and the minus correspond to a choice of one of these two vectors for the action on P tilde. Let's see. That's what I'm saying. So it turns out that if you look at the complexified cotangent bundle of X, that's isomorphic to the bundle of homomorphisms from S plus to S minus. So this gives you a way, I mean, this describes Clifford multiplication. So it tells you how cotangent vectors can act on elements of S plus, give you elements of S minus. And so the whole point of my saying this is that this is the symbol of the Dirac operator, which is one of the gadgets that shows up in the Seiberg-Witten equations. So if a four-manifold has a spin structure, then so there's an obstruction to having a spin structure. The obstruction is the second Stiefel-Whitney class of X. So a four-manifold has a spin structure if and only if its second Stiefel-Whitney class vanishes. And if it does, then they're in one-to-one correspondence with H1 with Z2 coefficients. Okay, so a four-manifold doesn't need to have a spin structure. It has a spin, well, for example, if it's simply connected, it has a spin structure if and only if its intersection form is even. On the other hand, there's another kind of related structure called a spin C structure, which four manifolds always have. So a spin C structure consists of rank 2 complex vector bundles, W plus or minus, with isomorphisms. So by determinant W plus, it's a top exterior power, or it's the complex line bundle whose first Turing class is the first Turing class of W plus. How's that? So let's give it a name, L, and such that locally these bundles, W plus or minus, are S plus or minus tensor the square root of L. So I need to tell you what this means, because I just said that a four-manifold doesn't have to have a spin structure, and so S plus or minus need not exist. So let me explain what I mean by locally here. So W plus minus are rank 2 complex vector. Oh, let's start with S. So here's a rank 2 complex vector bundle that arises. Its transition maps are the same as the transition maps of the principal bundle, P tilde. Now, of course, like I said, P tilde need not exist. But locally it exists in the sense that, you know, if you can cover your manifold with charts so that the intersections say contractible. And then, so then a bundle is given by transition maps. And so if P of X is given by transition maps Vij, then you can try to lift them to transition maps Vij tilde to spin 4, which of course you can do because this is contractible. So this is a fundamental group problem. But what makes you able to form a bundle is that the Vij's satisfy the cocycle condition, so that, you know, Vkj, Vji is Vki. And if you don't have a spin structure, if W2 is not 0, then these lifts that you get will not be compatible in the sense that they won't satisfy a cocycle condition like this. So W2 of X is going to be the obstruction to being able to find lifts like this that satisfy a cocycle condition. On the other hand, there's, if you have a complex line bundle, so its structure group is U1, and it has transition maps UI intersect UJ to U1. And you can ask whether a square root bundle means that you should be able to locally take a square root. It's just a circle. So, so you want to find, I mean, again, locally you can find square roots. And the question is, can you do this in such a way that they satisfy the cocycle condition? And so now if the line bundle L is characteristic, meaning if C1 reduces to W2 of X mod 2, so reducing to mod 2 cohomology, then the obstruction to being able to find such a square root is, again, that W2 of X should be 0, because if you find a square root bundle, then L is, C1 of L is twice C1 of the square root, which is 0 mod 2. So W2 is again the obstruction for this. And locally, so the obstruction to finding a bundle whose transition maps are Vij tilde tensor G to the 1/2, Ij to the 1/2 vanishes. So if you can find, it's twice W2. So if you can find a characteristic line bundle, then you can form such a spin C structure. So the obstruction to having Vij tilde tensor Gij to the 1/2 satisfy the cocycle condition. In other words, being able to find the Vij tildes in Gij to the 1/2, which satisfy the cocycle condition, vanishes, provided L is characteristic. So So there should be up to an action of H1 of X, the C2 coefficients. There exists a spin C structure like this for each characteristic element of H2 of X. So for each beta in H2 of X, C such that beta reduces to W2 of X mod 2. Okay, so spin C structures have Dirac operators the same way as spin structures do, except now you've got this extra bit of information you need to form the bundle. You've got this complex line bundle L as well as the spinner bundle. And so you get a Dirac operator D sub A from sections of W plus to sections of W minus for each connection A on this line bundle L. So let me denote the space of connections of the line bundle L by this symbol, which I don't know. So, okay. So given a four-manifold and a spin C structure, you can write down equations. So X, four-manifold, with spin C structure, say S, whose determinant line is L. Then for pair A, C in, so a connection on this line bundle L and a section of W plus, you can write down the following equations. That this section here should be killed by the Dirac operator, it's a harmonic spinner. And secondly, that the curvature, the self-dual part of the curvature of A should satisfy an equation I'm not going to describe. So it should, well, okay, I sort of describe it. There's a quadratic function of this section C with values in, see, this lives in, so the curvature of a connection on a complex line bundle is a imaginary valued two form on your manifold. And so this guy here lives in sort of I times omega 2 plus. And this is a quadratic function with values in omega 2 plus. So the important thing for us is not, so these are the Seiberg-Witten equations. And we're going to be interested more in their properties than what they are. So let me tell you something about the properties of the Seiberg-Witten equations. So first of all, the group of automorphisms of the bundle L, so this group is often called the gauge group of L. It's nothing more than maps from X to a circle where this circle just rotates the fibers. Okay, so let's denote it by script G. It's maps from X to the circle. And these automorphisms act on pairs A, C. So G acts on these pairs by G takes A to A minus G inverse dG, and C to just its action on the rotation on the fibers. And the key fact here is that this preserves solutions of the Seiberg-Witten equation. So if you have a solution of the Seiberg-Witten equations, G may take it to something else, but it's still a solution. So that one can form a moduli space where S again is the spin C structure, so we needed that to have both spinners and the Dirac operator. So this is the solutions to Seiberg-Witten equations for S after dividing out by the action of G. So this is going to provide our invariance for us. So it turns out that to obtain nice properties of this invariant, one needs to jiggle the equations a little bit. So what you do is you take this second equation and you add a perturbation term. Let's call it mu, where mu is just some self-dual two-form. And now, so now the first nice property. So for an open dense set of such perturbations, this is going to be a manifold. This moduli space is a manifold of dimension equal to a quarter. So let me, let's just write down. So C1 of L squared minus 3 times the signature plus twice the Euler characteristic of X. So there is a formula for the dimension of this moduli space, and this will be a manifold except at solutions which look like where this spinner, the section of W plus is 0. And these are called reducible solutions. So away from reducible solutions, one gets a manifold whose dimension you can calculate. And this means also that if this number turns out to be negative, away from reducible, then the only solutions you could have are reducible for this open dense set of perturbations. Okay, so here's some facts. So one, if B plus, so the positive, I guess there's no point in my explaining B plus at this point. So if B plus is positive, then if C1 of L is not torsion, so this is not a torsion element of H2 of X, then for a generic metric on X, or I guess for generic perturbation, mu, there are no reducible solutions. So unless you're dealing with a spin structure whose, so that C1 of this determinant line is torsion, or in the simply connected case, then if it's not 0, then we actually get a manifold of this dimension as the moduli space. And secondly, this moduli space is compact. Okay. Third, there are only finitely many spin C structures for which both the moduli space is non-empty and the calculated dimension is non-negative. So okay, so now I got to be careful here. So this statement means for small enough, so one has to be careful with the statement in case B plus is 1. It means for small enough perturbations. Okay. So given these facts, one can use this moduli space to get invariance of 4 manifolds. So let me say how. What is S? S is a spin C structure. It's okay. So it turns out that you can orient, it's possible to orient this moduli space by, so you can orient this moduli space by choosing an orientation, by orienting, well, actually I probably didn't say that our manifold X had to be oriented, but it does. So X has to be oriented, H1 of X needs to be oriented, and H2 plus. So once this is oriented, then you have generically you have a compact manifold which is oriented. It carries a fundamental class. And that fundamental class can be used to build invariants. For example, suppose the dimension of this moduli space, this formula that I raised, is 0. Then you have a compact zero-dimensional manifold, so you have a finite number of points, and it's oriented so you can count them with signs. So and that's the Seiberg-Witten invariant associated to the spin C structure S. If the dimension's positive, well, you can still do it. What you need is, you need to know something about the topology of the space of connections across sections of W plus. So this is all possible pairs that go into the Seiberg-Witten equations, divided out by the action of G. It turns out this carries topology. This is homotopy equivalent to CP infinity plus a torus. This is torus has dimension B1 of X. And you can use this topology to get invariants from the fundamental class of Mx. Okay, so in case, so here's the most important fact is that if B plus is bigger than 1, this actually gives you a diffeomorphism invariant. So in case B plus is equal to 1, we sort of get a diffeomorphism invariant. I'll talk about that later, not today. So what use is such an invariant? Well, one of the most important uses is to understand surfaces in a four manifold. So for example, suppose you have some S whose Seiberg-Witten invariant is not 0. And let's let beta be the Poincare dual of the first Chern class. So what I mean is the first Chern class of L, but I'll write S. And suppose that sigma is an embedded surface in X and of genus G. Then an inequality is satisfied. Namely, that 2G minus 2 has to be greater than or equal to the self-intersection of sigma plus the absolute value of the intersection number of beta and sigma. So this is one of the most useful properties of the Seiberg-Witten invariants. So let me give you some examples of manifolds that have non-trivial cyberwave invariance. So a complex surface is Kähler if it admits a metric so that G of J, X, and Y is a symplectic form. Did I say that right? Where's Andres? So it turns out that every simply connected complex surface has a Kähler structure. So let's just
Sorry, is sigma squared the self-intersection of sigma?
yeah,
Okay.
it's okay. Yeah. Every simply connected complex surface has a Kähler structure. Not only that, if you have a Kähler structure, there's sort of a canonical spin C structure. And each Kähler manifold has a canonical spin C structure. S sub k is called. And the first Chern class of S sub k is the canonical class of the first Chern class is, which is minus the first Chern class of the tangent bundle of X with, the complex structure like this. And Witten showed that if you compute the Seiberg-Witten invariance of this spin structure and its negative, you get plus or minus 1. And furthermore, if C1 squared of X is positive, so this is a surface of general type, then these are the only classes with non-trivial Seiberg-Witten invariance. And so it's useful to, okay, so this points out something I should say. So the Seiberg-Witten invariance of, so what do I mean by minus a spin C structure? I didn't ask that one. So what I mean is, okay. For a class beta in H2 of X, let's use the notation the Seiberg-Witten invariant of beta should be the sum over all S such that the Poincare dual of C1 of S is beta. How's that? So, and then really I mean to use homology classes or cohomology classes in that instead. So then the Seiberg-Witten invariant of minus beta will always turn out to be minus 1 to, well, either plus or minus the Seiberg-Witten invariant of beta, and the exponent here is the Euler characteristic plus the signature divided by 4. Now, you may think that we're losing a lot of information here by passing from spin structures to homology class, spin C structures to homology classes. But the focus of these lectures is going to be on simply connected manifolds. And remember, the spin C structures are in one-to-one correspondence with characteristic elements of H2 of X up to an action of H1 of X with Z mod 2 coefficients. And that's for a simply connected manifold that H1 is 0. So you lose no information at all in the simply connected case by talking about this.
What about the minimum over there?
Oh, minimal. I'm sorry. I probably forgot to put that in my notes too. So minimal means it's not a connected sum with CP2 bar. There should be no sphere of self-intersection minus 1. That will imply minimal. Okay, so it's useful to take these invariants and put them into a single unit. So let's write the Seiberg-Witten invariant of X. So we'll think of it as an element of the integral group ring of the second homology. And so these are finite sums of integer multiples of elements of H2 of X, where we think of H2 of X now as multiplicative. So we'll write it as sum Seiberg-Witten X of beta times T sub beta, where beta runs through all characteristic homology elements, characteristic elements of H2 of X. And so in particular, notice I'm saying that this sum is finite. So this follows more or less from one of these facts, fact number 3 that I wrote before. This has to be, for B plus bigger than 1, this sum is finite. Oh, okay. So what is this saying? So this is saying, for example, in this case here, for minimal surface of general type, simply connected, it's saying that this Seiberg-Witten invariant is T sub k x plus or minus T sub kx inverse, where T sub kx inverse is the multiplicative element corresponding to minus kx. Okay? And for the K3 surface, K3 surface is a manifold with C1 equal to 0. So the canonical class is 0 in that case. And here's a good exercise, is to use the adjunction inequality to try to show that there's no other elements of H2 of the K3 surface that have non-trivial Seiberg-Witten invariants. So we know that the characteristic class has Seiberg-Witten invariant plus or minus 1. So let's say we choose orientation, so it's plus 1. So you know that Seiberg-Witten invariant of K3 of 0 is 1. And by using arguments only involving the adjunction inequality and sort of knowledge of how to represent homology classes of K3, you can show there are no other non-trivial Seiberg-Witten invariants. So you could, as an element of the integral group ring, you could write the Seiberg-Witten invariant of K3 as 1. Meaning Seiberg-Witten of 0 is 1, and T sub 0 is 1 multiplicatively. So it's 1 times 1. Okay, so I've got 10 minutes to tell you what the topic of this lecture is about. So it's really, it's about cliff tops. And so I want to talk about gluing theorems. The Seiberg-Witten invariant. And so the way I'd like to try to talk about calculating Seiberg-Witten invariants in future lectures is by cutting and pasting and pieces that we know and using this gluing theorem I'm going to describe. So this theorem, in its most general sense, is due to Cliff-Taubes, but there are also versions due to Morgan, Morofka, and Szabo. And also due to Doug Park. So this theorem tells you what happens when you have four manifolds with boundary of 3 torus and glue them together. So so it turns out that such four manifolds also have Seiberg-Witten invariants. But, so by which I mean four manifolds whose boundary is a 3 torus. But they no longer have to be elements of the integral group ring. They can now be, they're now formal power series. So such manifolds have elements in, I don't know, I guess you should write it like this. And the theorem of Taubes is that if X is a union of two four manifolds whose boundaries are 3 torus, so let me denote it this way. And so is there a B plus condition? Does anyone remember, is there a B plus condition? So then is there, for this gluing theorem, is there a B plus condition, do you know? It must, no, there's not. It should be positive anyway, B plus bigger than 0. And suppose that there's a cohomology class. So, alpha in H upper 2 of X, it should be a real cohomology class, which restricts non-trivially to the boundary T3, restricting sorry? Yeah, each side they should be positive. Yeah. How's that? Is that right? No. You don't need that. Because it's going to work if you pull out a neighborhood of a self-intersection 0 torus. Okay, let me say. So then, then the Seiberg-Witten invariant of X is J1 star of the Seiberg-Witten invariant of X1 times J2 star of the Seiberg-Witten invariant of X2, where J1 and J2 are the inclusion maps of X1 and X2 into X, and so J1 star is the induced map on homology, and then again induced on the, on this ring of formal power series. And a prime example is this case. I'm going to only talk on that side. So a prime example is that the Seiberg-Witten invariant of D2 cross T2 is 1 over T minus T inverse, where T is the element of the group ring corresponding to the T2. Okay? So let me give you an example. Oh, here's one other fact. There's an addendum which says that if, so this is due to Doug Parr, so that if you look at the co-kernel of if T is a self-intersection 0 torus contained in X, and you look at the co-kernel of the inclusion of the restriction of H1 of X minus the neighborhood of T to H1 of the boundary of that neighborhood. If this has no torsion, then it says that the Seiberg-Witten invariant, this relative Seiberg-Witten invariant, is equal to the absolute Seiberg-Witten invariant of X multiplied by T minus T inverse, where again, this is the same T. So this is almost the same as saying the Seiberg-Witten invariant of X is the Seiberg-Witten invariant of X minus NT times 1 over T minus T inverse. It's a little stronger. So let's use this to calculate Seiberg-Witten invariants of elliptic surfaces. So let's let En be the elliptic surface over S2 with no multiple fibers. Minimal and C1 squared equal, how do I say it? Euler characteristic plus signature over 4 equal to N. So what is this? So E1, you can think E1 is CP2 blown up 9 times. So another exercise is to use cubics in CP2. Use cubics in CP2 to see that after you blow up 9 times, you get a fibration over S2, whose fiber is a torus. Then En is the fiber sum of n of these. By fiber sum, I mean remove the neighborhood of one of these tori from each piece and glue together. I guess in the middle pieces you need to remove 2 tori. Okay, so I've just claimed, so it turns out that E2 is the K3 surface. And here I've claimed that the Seiberg-Witten invariant of the K3 surface is 1. So this tells us that if we remove a fiber, the neighborhood of a fiber, we're going to get T minus T inverse. Because this times 1 over T minus T inverse is 1. And now, But, so E2 is the union. It's a fiber sum of two E1, so it's E1 minus the neighborhood of a fiber union with E1 minus the neighborhood of a fiber. So we know that its Seiberg-Witten invariant is 1, which is going to have to be the Seiberg-Witten invariant of E1 minus the neighborhood of a fiber squared. So this is again 1. Okay, so now let's try to compute the Seiberg-Witten invariant of E1. That's the Seiberg-Witten invariant of E1. So this is a little, again, a little touchy because this has B plus equal 1. It's just got one super. Times the Seiberg-Witten invariant of this neighborhood of a fiber, which is T2 cross D2, so that's 1 over T minus T inverse. But we just saw this is 1. So this is 1 over T minus T inverse. Okay. So the Seiberg-Witten invariant of E3, that's, well, E3 is E2 minus the neighborhood of a fiber union with E1 minus the neighborhood of a fiber. So the Seiberg-Witten invariant here is the Seiberg-Witten invariant of E2 minus the neighborhood of a fiber times the Seiberg-Witten invariant of E1 minus the neighborhood of a fiber. I'm just assuming all these inclusion maps are the identity now. So the Seiberg-Witten invariant of E2 minus the neighborhood of a fiber, we calculate here, it's T minus T inverse. And the Seiberg-Witten invariant of E1 minus the neighborhood of a fiber, we calculate it here, it's 1. So we get T minus T inverse. So now it's easy to see how you induct to compute the Seiberg-Witten invariant of En for every n. And what you'll get is T minus T inverse. So it's the induction step. En minus 1 minus the neighborhood of a fiber times 1, which is T minus T inverse to the n minus 2. Okay, again, T is the element in the group ring corresponding to the fiber F. So this is saying there's no other classes that have non-trivial Seiberg-Witten invariants. All other classes have Seiberg-Witten invariant 0. And you can calculate what the Seiberg-Witten invariants of any multiple of a fiber are just by expanding this. Okay? So I think I'll stop here because I'm out of time. I had hoped to talk about surgery. So maybe I'll begin my next lecture by talking about a little bit about surgery because we're going to need that to talk about not surgery. Maybe all kinds of surgery next. So I'm sorry this seems a little disjointed. I honestly don't know how to give this lecture. And maybe that's apparent now. I hope the rest will be more focused since they will cover much less material. At any rate, I'll make these notes available, so at least if nothing else, you have printed copies. Thanks.